Professor Chien-Yuh Yang is currently a professor in the Department of Mechanical Engineering at the National Central University, Taiwan, and also served as the president of the Taiwan Solar Energy and New Energy Society. He received his PhD from the Penn State University in 1994 and stayed at the same university as a postdoc associate following his PhD until the next year. Then he went back to Taiwan and joined the Department of Mechanical Engineering at National Central University in 1995. His current research interests include air conditioning and refrigeration, heat exchange design, solar energy, electronic devices, cooling, two-phase heat transfer enhancement, and microscale heat transfer. His research has a strong connection with related industries. He has conducted more than 100 heat transfer-related research projects, most of them well supported by the industry companies. He has cooperated with local companies on the studies of plate heat exchanges, and continuously for more than 15 years. He participated in the organization of a number of international conferences and workshops. He has co-authored more than 100 journal articles and conference papers and has more than 10 heat exchanger-related patents. So we are very happy to have Professor Yang to give the lecture today. And Professor Yang, please.
Okay, thank you. Thank you for Professor Yip's very detailed introduction of my experience. And I'm working for the heat transfer, majorly for heat transfer and for the exchanger design. And before, originally the major of my research is for the electronic device cooling and some for the computer or electric vehicles. And about 3 years ago, the NSPO in Taiwan, they contacted me to help them to design for the cooling system of the communication satellite, because of their satellite, the heat dissipation of their satellite increased very drastically from several watt to several kilowatt in the coming several years. So starting from this project, so we think about how to apply our heat exchanger design on the heat cooling system of the communication satellite. Okay, so then I change to my PowerPoint. Okay, and my name is Chien-Yuh Yang, as just introduced by Professor Yip, and these are my students, and this is a researcher from the NSPO. And
we cannot see the slide. Can you?
Can you see?
We are only seeing the cover page.
Only cover page, yes. Now it's just cover page. This is the page, right?
All right, yeah.
Okay, that's good. And this project was supported by the National Space Organization, and starting about 3 years ago, and now it's just finished, and we are talking about the next project. Okay, now we are making a brief introduction of the communication satellite, because most of the audience, I think, is just junior students. And then we are going to move our communication system from the currently for 4G or 5G to the beyond 5G or 6G, and then it used the communication satellite as the interaction, the interaction point. So that is just a schematic diagram of the communication satellite. This is Earth, and then the communication satellite circulate around the Earth continuously, and the signal from anywhere of the Earth station, then they transfer to the satellite, and then they go back to the Earth station. So this is the communication satellite, and the heat dissipation from the radar for the signal transfer is increased very fast, and it was just several watts, but now it's increased to about several kilowatts. So now how to dissipate this heat is the problem. So this project is talking about the new satellite were developed by the NSPO, and their design spec is the wireless satellite goes through around the Earth. So while it's passing through the top of the Taiwan, then the signal will connect with uplink to the satellite. This is the ground station of the Earth. Then while it moves out of this range of Taiwan, then it will disconnect it. So while the satellites connect to the Earth station, then the radar will work. So the power will be very high. And then after it leaves this one to the other side, the radar will not work. So there's very low power generation. So the heat dissipation requirement for about 10 minutes, just the connection to the Earth station is about 500 watts. And while it's not in the connection, under connection is leap out of the top of Taiwan, then it's just very low. It's just about 50 watts. And its time duration is about 90 minutes. So it is our purpose to design for a system for this one. So this is the schematic diagram of the radar. So there's two antenna. One is the transmit antenna, the other is the receiving antenna. So now we are going to design the pulling of this antenna circuit board. And this is we just said is a periodic heat source. And the maximum temperature we hope is under 60 degrees. So this is just the radar module. And in this module, we have the two TX, the transmitting antenna, and the two receiving antenna. And the size is about 100 centimeter by 100 centimeter. And then we can cut this side into this one. So this is the PC board. All electronic device below this antenna, and then we put the cooling system on the top of the antenna. And then, so this is the top view of these two antennas. One is the 360 by 360 millimeter, and the heating source is about 288 by 288. And the other one for the receiving antenna, the total size is the 440 to 60, and the heating source is the 340 to 180. And so this is just a picture of what you see for the antenna. So the heating condition of these two antennas is here is the heating area. So we just say 288 by 288, and the other one is 180 by 340. And for each module, we have two TX and two RX. And the heating rate at the peak 10 minutes is 50 watt for the TX, and 275 watt. This is 500 watt for TX and 275 watt for RX. And the off peak is the 50 watt for TX and the 27.5 watt for the RX. So if we really want to cool this system, then we can, the most easiest way is to cool it directly. So where it's generated 500 watt, and we can design a radiator to dissipate the heat with the 500 watt capacity directly. And then where it in the off-peak period, it's just 50 watt. So then the radiator will be too large for them, and it costs the not economic design. So we're thinking about we use the phase change material, and we can use the phase change material to absorb heat, dissipate at the peak hour, and then we cool it evenly through the entire 100 minutes. So where we make a very easy calculation, then we can calculate it for this one 500 watt and 50 watt, 500 watt for 10 minutes and 50 watt for 90 minutes. And where we use the uniform cooling, we need just 95 watts. So we need just a very small radiator to dissipate the 90 watt heat. So this is a schematic diagram of the temperature variation with time And we can see that this is the dot line is the temperature variation we expected without phase change material. So the peak is very high, and then cool it down, and then heating and cool. And while we use the phase change material, while the heat generated, then part of the heat was absorbed by the phase change material to let it from the solid to change to the liquid. And then while in the off-peak period, no heat generated from the fishbowl, so then the heat transfer to the cooling liquid and then to the radiator. So the peak temperature will be much lower than that without PCM. So here's the cooling system design. So we think about, so this is the generation chip. Then at the peak period, this is the PC ball, and we use the heat changer. So this is a heat changer, and we fill with the phase change material. Then at the peak period, the heat generated from the PC ball and the chip, then it partly transferred to the cooling fluid. So this is cooling liquid, and then part of it transferred to the PCM. And while in off-peak period, then the heat transfer from the PC board and the chip transfer to the cooling liquid, and also the heat transfer, the heat from the PCM transfer to the cooling liquid. So this is the basic design concept. So for this concept, the first step, we have to make the first approximation design. So we use we call this the thermal resistance network. We calculate the network at each step and make a brief design of the heat changer. And the next we use the numerical analysis to refine this design. And finally, we use the experimental measurement. We set up a test system to measure the performance to see how much difference with the actual heat transfer performance to the initial design. So the first one, we choose the phase change material. The most important one is to find the phase change temperature. Since the maximum temperature allowed for this system is the 60 degrees, so we choose the phase change material, and with the phase change temperature lower than the 60 degrees, but not too low, because if it's too low, then it will be a problem for the cooling. The cooling performance will be very low. So then we choose the two kinds of the phase change material. One is the lauric acid, and the other one is the tetradecanol. I'm not really don't know how to read this. It's very difficult for me. And the temperature for the lauric acid is 44 degrees Celsius, and the other one is 37 degrees Celsius. And this is all his property. So the latent heat, one is 178, the other one is 288. Of course, the higher latent heat will be the better, because we need less amount of the phase change material if the latent heat is high. And we hope that the solid density is higher, so the volume will be smaller, and higher thermal conductivity, so the heat transfer performance will be higher. So for both the liquid thermal conductivity and the solid thermal conductivity, this one will be better than this one. And the thermal expansion coefficient, this means that what is the change from the liquid to the solid, the volume change, how much is the volume change. So then we use the property of these two phase change material, and then we calculate how much of the phase change we need for this system. So the amount of the phase change material, this means that we have to transfer the heat. The transfer heat, including the heat transfer rate. This is not heat flux, heat transfer rate. I make a mistake. Heat transfer rate times the time period at the peak period plus of the peak period, and over the latent heat. the latent heat of these two phase change material. So then we calculate this amount of the phase change we need, which material we need, and that is for the two heat changers. One is for Tx, the other one is for Rx. So for the Tx, while we use this one, we need 1.0 kilogram, and if we use the lauric acid, we need just 1.36 kilogram. And then for the Rx, one is 0.959 and the other 0.75. So the mass of this one will be less than this one because this is smaller, this is larger. So this is the first design concept, and then we use this is the stack plate. We use the aluminum. No, we use the stainless. For this test, we use the stainless steel piece for this one, and then we use the copper tube. This is the copper tube, and we use aluminum fin. So this is a typical fin tube heat changers. And if you cut from this side, then we can see this one. So here is the cooling pipe, the copper tube, and here is the fin. Here's the fin, and the entire is heat changers, and we fill the phase change material inside, and the bottom it's attached with the Rx or Tx. So this is the heat source, heat generated from these two, and the transfer to the entire heat changer, and the transfer to the PCM and to the cooling liquid. So where we want to calculate the fin space, then we use we call it the thermal resistance network. This is very popular for the heat transfer field, but I'm not sure if for the other one, maybe you're not familiar with this kind of the thermal resistance network. So the definition of thermal resistance is the temperature difference over heat transfer rate. This means if you want to transfer certain amount of the heat of the heat, then how many degrees of the temperature difference between these two objects. For example, for this one, so this is this part, the enlarged view of this part, the bottom part. So the heat is from the bottom, and then so this we call this the T base, the base temperature. Then it transfers to the fin. So from the T base to the fin, there is the thermal resistance, and then it transfers to the PCM. So we have another thermal resistance. We call this this is the convection for liquid thermal resistance, liquid PCM, or the conduction for the solid PCM, and this is the conduction from the fin. So we can use some existing correlation to calculate the thermal resistance, and the total thermal resistance equal to the summation of all this resistance. And it is also for this part to the cooling tube. So this is the cooling tube, and then we put the cooling fluid inside the tube. So the heat transfer from the PCM through the fin and to the cooling fluid. So this is also another thermal resistance network. So we summarize all of these each thermal resistance. Then we can calculate the heat transfer area we need for these heat changers. So the heat transfer path will from the antenna to the base plate and to the fin to the PCM. And the other one is from the antenna to base plate, and to the cooling fluid, or from the PCM to the cooling fluid. So this is the thermal resistance network design, and we make the detailed calculation of the thermal resistance, and then we find the relation between the fin space and the base temperature, and we can find while we use the smaller fin space, then the base temperature will be lower. We'll have a lower base temperature because if we use the smaller fin space, then we will have more fins for the heat transfer. Then the temperature of the base will be lower. And originally we select for the fin space of 4.5 because if you select too much fins, then it will be heavy. This will be heavy, and we can put less PCM because the most of the volume will be occupied by the fins. So the can be allowed for the PCM volume is smaller, and then we can just store less heat. So we choose this one, 4.5 fin space as our first approximate design. But unfortunately, we cannot find the commercial product with the fin space with 4.5. So we just choose the most cost one. Is for the commercial product is the just 2 millimeter fin space. So this is original heating area. Then we choose the commercial product very close to this one, 288. We choose this one, 279.4 by 280, and the other one for the RX, the original size is the 180 times the 340, and then we choose the other one is 177.8 times 340. So the estimate the heat change weight, if we use our calculated result, it will be 1.46, but we use the commercial product, it will be 1.56, a little bit higher than this one. And also for the RX, originally is 1.1, and then after use the commercial product is 1.17. Okay, now then we put the PCM into the heat changers, and then we calculate the fin efficiency and the surface efficiency, transfer coefficient, and the thermal resistance. So we use the thermal resistance network to calculate all these performance parameters one by one. And for the TX, then we can find the originally calculated base temperature is the 48.1, but now while we use the commercial product, then it reduced to 41.3 because in our original design, the fin space is 4.5 millimeter, but now we use the 2 millimeters. The fin space is much smaller than this one, so the base temperature is lower than this one. And while we use the lauric acid, because the melting point of lauric acid is higher than that of this one, so the base temperature will also higher than this one. This is 55.9, and the actual heat changer will be 48.5. And also for RX, so it changed from 34.8 to 40.1, and while you use another PCM, it will be changed from 52.4 to 47.2. Okay, now this is the heat changer, and we asked the company to make it for us. And this one, so here is the engineering drawing. I think this is very familiar for a mechanical student, but probably not familiar with other students. So this is the weight, this is 360, and the height is the 288. So this is for the TX. And this is the cross-section view of this one. So here is the tube. This is the tube. The thickness is the 22 millimeters. And this is another view, the cross-section view of this one. This is the cross-section view. So you can find each fin. And this is enlarged view of the fin, enlarged view of this area. So this is the cross-section V. So it's enlarged. So the fin space is the 2 millimeters, and the fin thickness is the 0.12 millimeters. This is the commercial product for the air conditioning. And also the height is the 22. This is the same as 22. And the fin, the tube diameter is the 19.05 millimeters. And the other one is for the RX, for the receiving antenna. So it's similar to this one, but the size is not the same. So this is 424 and 187. So this is another heat changers. And now we are going to set up a test system. Okay, I have a cup of water. So this is our heat changer. So this is a schematic diagram of heat changers, and this is the fin, and this is the PCM, and the cooling liquid going on this side and out on this side. And in the bottom of the changers, we attach two plate heaters. So this is heaters was made by Subtractive, and the inside the electrical heater inside. We attach this plate heater on the top. We use this one to simulate the heat generation from the chip. And then we put a video camera to monitor the phase change of the PCM. So the PCM will change. Well, it's melting, the color will change, so we can know at what time, how many percent of the PCM has melted. And while in the heating test, we didn't put the cooling liquid in, we just used the heating. And for the cyclic test, we will include the heating and the cooling. So here is the temperature measurement from the top view of the RX. So this is the RX, and this is the bottom view of the RX. This is the bottom side, this top side from top, this from bottom. So from the bottom, we have two plate heaters, and we measure 7 points at the top. One is the center of the heating surface, and the 2 and 3 in the side of the plate heater. And the 4, 5, 6, 7 is the one side of the heating plate, or it's attached on the bottom surface. And in the top side, we measure the center part, and then 0.9, 10, 11, and 12 to measure the temperature variation along this way. So totally, we measure the 12 points. And it's 7 on this one, 4 on this one, and the 1 is for the air. So this is the measuring results. So originally I have a video. Okay? No, it cannot play this video. Okay, so while we can see the temperature change. Here is the from the top view, the 0.9. So the 0.9 is this is the red one. So this line, the red one is 0.9. So we can see the temperature change from 0 to about 1 and 10 seconds. So the temperature increase. This means that it's at a single phase range, because in the single phase solid, where the heat put into the solid temperature will increase. And then at a certain point, the temperature will not increase so much, because part of the solid melt and get to liquid, and it absorbs heat, the latent heat. So the temperature will not change very much. And up to here, it completely melt. So the temperature will increase again, because this is just a liquid. So temperature will increase again. So at the 0.9, it's very close to the 0.10, because our heater is on the top bottom on this side. So both the 9 and the 10 is very close, and it's starting to melt at around 2 minutes. This is 1 and 10 seconds, around 2 minutes. And to this one, this 460 seconds is around 8 minutes. So it's 8 minutes completely melted. But for the side area, T11 and the T12, 11 and 12. So it start with complete later than this one. So it's about 7 720 seconds is about 12 minutes to completely melt at this point. So this is the, no, I cannot play this one. So if we complete this, you will see that one, while the time change is will be made from here and then expand to the corner side. But even though we cannot see this video and we have some other pictures. Okay, this is the picture. So from the 0 minute, it's just the start, and then this is 5 minutes. From the 5 minutes, we can see some of the area near the fin. Okay, here's near the fin and near the tube is the starting to the phase change to liquid. The dark area means it's the liquid, and the light area, that color is the solid. So by 8 minutes, most of the area is melted. So this is melted, this is melted, and the white area is melted. And after about 10 minutes, it's completely melted. So this is for this PCM, the time, the melting time. Okay, now we are thinking about the temperature measurement. So at the bottom, here is the temperature 1, 2, and 3. So T1, T2, and T3. So for this one, this is Rx. The T1, T2, and T3. So this is the T1, T2, and T3 is 1 minute, 5 minutes, 8 minutes, and 10 minutes. So it's very close. It's from 1 minute to 8 minutes. The temperature at the bottom of this is very close. So very close. And around 10 minutes, because the center part is already completely melted, so the temperature increased. So it's about 2 degrees. No, this is from the 1 minute to 8 minutes. The temperature difference between the entire bottom plate is about just 2 degrees Celsius. And the average bottom temperature, the average of this bottom temperature is about 43.6. And the phase change temperature of this phase change material, this one is 37 degrees Celsius. And for the other point, from 4, 5, 6, 7, this one is the edge. It's the edge. So it's the temperature. Yes, because the melting time of the PCM at the edge is not the same, not as that at the center part. So there is some temperature difference from the P4, P5. This is 4 and 5, and 7 and 6. So the temperature difference between this is a little bit higher, but not so much, just about 5 degrees Celsius, not very high. And this is the other one, the other phase change material. We use the lauric acid. So it's similar to this one. So this is the melting point. So the phase change from the about 2 minutes, or should be around 3 minutes. Most of it from 3 minutes. Then to the about 10 minutes. And it's completely melted around 12 minutes. It's slower than that for this one. Slower than for this one. So this is for the lauric acid melting time. And the bottom temperature of the lauric acid heat changes is very similar to this one, but this here is the very high temperature at this point. At this point, and we find that with the contact of the heat changer to the heater at this point is not to the some couple of this point is not very good. So here is a very high contact resistance. So temperature of this one is much higher than of the 0.2 and 0.3. So this is the expanded problem. And then the other one is similar to the previous one. It's about 3 degrees Celsius difference. and the average temperature is about 48.4, and this is because the lauric acid melting point is 44 degrees Celsius. So the melting point, the average bottom point is higher than that of the other one. So this is 48.4 degrees Celsius. The other one is the 43.6 degrees Celsius. Now we use the next one. We use the numerical simulation. So this is I use the Cradle CFD. I heard this. I'm not a numerical guy. I didn't work for a numerical simulation. This part was one of my colleagues helped my student to work for this one, and he said that the Cradle is very popular for space design. I'm not sure it's correct or not. And they use the Cradle CFD and to simulate the heating condition. At the heating condition, no cooling liquid passing through the tube, so it will be derivative. And then the side of so this is heat exchangers, and we cut this part. This is just a piece of fin. So this is a piece of fin, and then this is the tube hole. And we cut this part as our control volume. So this part in large view, this part is this one. So this is the tube, no liquid, so it's a adiabatic wall. Then the side of this control volume, because all is symmetric, so the side wall also adiabatic. And the upper part is open to the air. It's open to the air, and the bottom part is constant heat flux. So this is the phase change material for the entire system. And then we use this system and to calculate for the heating condition. So at 1 minute of the heating, so it's just start. So the dark blue one is solid, and the yellow is the air or the gas outside of the PCM. And after 5 minutes, part of the PCM melted. The light blue one is the liquid, so this color is liquid. So part of the PCM melted at the bottom side because the heat from the bottom. And then after 6 minutes, the liquid layer increased. And after some minutes, most of the PCM is melted, and it's the part of the PCM on the top side also melted. So the liquid contact to the air directly. So it will make a mixing of the liquid and air because both of them are fluid. So after 10 minutes, the entire PCM melted completely. So this is the numerical simulation result. And we can also see the average bottom temperature for this one. So the phase change temperature of this one is 37 degrees Celsius. This is 37 degrees Celsius. And the average temperature is changed from the room temperature to the phase change temperature. Then it's increased to the next one is around 10 minutes. It's about 42.7 degrees Celsius. So this is the maximum temperature for this PCM at the heating condition for RX exchanger. And we can compare this one with the experimental results. So this is the numerical simulation, and this is it. Yeah, I think I make a mistake. This one, this is experiment, not the numerical. Sorry, experiment results. So this is one. This is numerical, and this is experiment. And the maximum temperature, the max temperature at the 10 minutes, because we wanted to heat 10 minutes, so it's about 47.6 degrees Celsius for only experiment. And while we use the numerical simulation, it's the 42.7. So the difference is not much, just 0.9 degrees Celsius. And in our first approximation calculation, we used the thermal resistance network. The temperature is the 40.1. It's also not much. It's all these differences set because just 2 degrees Celsius for the approximation calculation and less than 1 degree Celsius for experiment and simulation. So both the simulation is okay, and also the post approximation. And this is the test is under at the ground, so the gravity condition is 1G, and because we are not able to test it at 0G, even though we go to the parabolic flight, but the time is just a couple seconds, so it's not enough for this kind of experiment. So we use the simulation to compare the difference, between 1G and 0G. So when we use the 1G at the ground, then we can find at the 10 minutes, the temperature is 42.7 degrees Celsius. So this one is the same as this one. And while we use the 0G for the satellite, it's about 41.1 at the 10 minutes. So not much difference, just 1.6 degrees Celsius. And both of them are less than our design requirement for the 60 degrees Celsius. Okay, now the other one, we compare the different PCM. So this one, for the lactic acid, because the lactic acid change temperature is 44 degrees, and for this one, it's just 37 degrees. So this is higher than this one. So the temperature of both numerical simulation and the experiment. So this is the numerical experiment, 51.3, and this is the 42.7, and this is 43.7 by experiment. So you can change, you can see this is the numerical result. The red line is the numerical simulation result, and the blue line is the experimental result. So the 10 minutes, the temperature difference, this one is just 1 degree, and this is about 3 degrees Celsius. Okay, now we move to the last step for the cyclic test. The cycling test, we use the 10 minutes heating for 500 kilowatt, and then 100 minutes for the cooling by the air natural convection. So we use the pump to pump working fluid through the cooling pipe, and then we pump it to the heat dissipation panel. In the satellite, this could be a radiator, just use the radiation because there is no air in the satellite. But now at the ground, we cannot use the radiation because the environment temperature is very high, so we cannot use the radiation. So we change it to the natural convection. So we use this is our test chamber for the natural convection test chamber. This is a standard for the natural convection. So here's the test plate. We put the heat exchanger on this one, and here's the open window to let the air can move freely inside the chamber and freely outside. And so we use the liquid cooling system to move the heat from the heat exchanger to the heat dissipation panel. And here is the actual experiment setup. So this one is the RX, and this is TX. And we put the pump here, and then put the cooling liquid through these two heat exchangers and go back to the pump. And we use the two copper plate as the heat dissipation panel. Copper tube. So we put the liquid inside the tube and then pump the liquid through the heat exchanger to carry the heat into the heat dissipation panel, and then the natural convection inside of this one to decrease the temperature of the liquid. So here is the piping. So the pump pumps through the liquid to the RX first, then to the TX, then through the heat dissipation panel, then go back to the pump. And we measure, the first one is the temperature get into the heat changer, and then we measure the dissipation panel surface temperature 0.2 and 0.3 near the tube, and also 0.4 and 5, 6, 7, 8, 9, 10. The temperature after heat dissipation. And then this is the enlarged view of this dissipation panel. So this is the inner side. This is outer side. So we measure the temperature of the inner side 12, 13 and 14, 15. So we measure all totally 15 point temperature difference. Okay, now this is the temperature we measure. So it's so we can see this one. This is for this phase change material, and the red one is for the Rx. The blue one is for Tx. So this is for Tx. This is for Rx, and we see that one for the Tx because the heating rate is the 500 watt, and for Rx is 275 watt. So the heating rate, the Tx is much higher than that of the Rx. So the temperature is higher. So we can see for Rx, the temperature change, this one, from about 26.7 to the highest one is about 43.7. And for the Tx, the lowest temperature is about 31.1 and highest is about 60.1. And if you change it to the lauric acid, because the lauric acid temperature is higher than this one, so the temperature also higher than this one. So for the Rx, it's from 27.8 to about 47.8, and for the Tx, it's from about 32.3 to 64.8. It's 64.8. And also we use the numerical simulation to find the temperature variation for the cycling condition. So this is the simulation result. So the green one is this phase change material, and the blue line is the lauric acid, and the red line is no PCM. If we don't put PCM inside the heat changers, so there's no PCM. So we can find for this one. So this is the Tx. This is Tx. This is Rx. So for the Tx, the temperature change from with no PCM, it changed from 42.3 to 408.2. So temperature much higher than the upper limit of our design. So if you don't use the phase change material, the heating surface temperature will be very high, up to more than 400 degrees. It's also the same for the Rx. For the Rx, it's more than 300 degrees, about 311. And while we use the phase change material in the heat changers, then it decrease the maximum temperature very large. It's just from the 300 degrees reduced to 51 and 42. And for the Tx, from the 400 degrees reduced to 65 and 57. So we can see that the PCM is very useful to reduce the peak temperature of the satellite radar system. So finally we make a summary of our lecture today, and we design a cooling system for the transmit antenna and the receive antenna cooling, and with the POE, the electrical source, and we hope that the T maximum is less than 60 degrees. And we choose these two PCMs as the store energy for the heat and to reduce the T maximum. And firstly, we use the simulation network to design the heat changers, and then we use the equipment measurement for the validation of the first approximation design. And lastly, we use the numerical simulation and for comparison to compare with the experimental results. So this is the final result. We summarize it here. So this is the first approximation. This is the simulation. This is the experiment. So for the first approximation, we design this one. If we use this friction material, it's the 40.1 and for TX 41.3. And for the simulation, it's 42.7. And this is 57.2. And the experiment shows a little bit higher than this of simulation. And also, if we use the lauric acid, then this is 47.48 and 51.65. And this is a little bit lower than this one. So the numerical simulation is very close to our practical experimental results. So this is our lecture today, and I think most of you was not in National Central University. National Central is a very beautiful university, and has been selected as the most beautiful university in Taiwan. So I hope all of you can have the chance to visit our university. Thank you for your attention.
Yes, thank you, Professor Yang. A very detailed engineering talk. It's really engineering talk. Any question from audience? First, I'd like to field a couple of questions if there are any. You could raise your hands, or you could just turn on your mic and ask questions. I don't see any hands yet. So I might ask the question, Professor Yang.
Yeah.
I assume that this is you do this for the SAR, the synthetic aperture radar system. Is that right?
Yeah. Yes, it's SAR. Yeah.
Yeah. Okay. And do you know when you have to use that? I mean, when it's supposed to be launched? We are very interested in that question.
Actually, I'm not familiar with the satellite because I just contacted for just 2 or 3 years. So I'm not with this one.
Okay, seems to be that you are doing a lot of pumping in there. Right?
Yeah.
So the next question is, what's the lifetime? I mean, you might have a leakage and that sort of thing, making the whole satellite very messy.
Most of the satellite they use the heat pipe. It's a passive type heat transfer, but the amount of heat pipe can transfer. The heat amount of heat pipe is very low, so it's not enough to transfer the several kilowatt. So then we think about the pump, the active side method. Then normally the lifetime of the pump in the ground test is more than 20,000 hours. 10,000 hours, yeah, more than 27 hours.
So your estimate is 20,000 hours.
20,000 hours. So it's about 3 years, right?
3 years. All right. So
okay, good. Not 3 years. I think more than 3 years.
Well, I mean, because you operate, each orbit you operate for a few minutes, so so it's
it stops
periodically. Yeah. So I can see some hands already. So first, ask Grant. Grant, your question.
Yes, thank you. Very good talk.
Yeah.
I was curious about the size of these devices and if you can miniaturize them. How small can you make them? Have them be effective?
Yes. This is the next step of our research, and then we use the fin tube exchangers. Yeah, this one is me show you. There it is.
Well, Professor Yang used to work on refrigerator. You know how big that might be.
Yeah. So this is the fin tube exchangers, and then the next step we will use the other kind of fin tube exchangers. We say that the one is the brazed aluminum. It's much lighter than this one. This one is more than 1 kilogram. The size is okay because the SPOs told me the size is acceptable because they have enough space for this one. But the weight, they hope they can as less as possible. So while you change the heat change to the other one, the weight will be just half, reduce half of this one, about 500 grams maybe. So then this is the next step of our research. So we also hope we can reduce the weight and reduce the size of these exchangers.
So what's the total area? Total
area, let me see. So it's This one, 279, 20 to 80.
So it's a 30 centimeter by 30 centimeter,
yeah,
right?
about
Yeah.
so and the thickness is 2 centimeters.
You know, there's a CubeSat SAR satellite called ISI, which is a CubeSat. So you have to miniaturize it to fit into the CubeSat.
Yeah, so if we, but for the CubeSat, I think the heat transfer rate is lower than this one. It's much lower than this one. For the single component of this one, we tested for 500 watt, 500 plus 275, so it's 775 watt. So I think for the CubeSat, the heat detection is much smaller than this one.
It just depends because you also have smaller room for exchange, so you can have temperature gradients across small distances.
Yeah.
Grant, you have other questions?
No, that was good. Thank you. Appreciate it.
Yeah, thank you.
Thank you.
We have another question by Lin Chi-Hong.
Okay, so good morning, Professor. So I have two questions. So first question is, so we know when something material they are heated by the heat, the density will lower. So they'll be right side.
Your speaker has some noise.
Hello?
Yeah, some noise.
Oh, okay.
Somehow is that they're trapping in there.
Oh, okay. So I repeat again. Sorry. So my first question is, we know when something material they are heated by the heat, the density will lower a little bit right side because of the convection, just like water and air. So my question is, in this heat exchanger itself, will this PCM also appears a convection? So if they have a convection effect, so how do they effect for the heat dispersion and the performance of this exchanger? So this is the first question. Thank you.
Okay, sorry, because you just have some noise. I didn't hear your question very clearly. So if I'm not correct, let me know. So you asked about the heat transfer path, right?
Yeah.
This one. So I assume this is open to the air, and you say this will be a convection. Is that correct?
Yeah, so will there appear a convection when the PCM are heating by the plate?
Okay. So because of the convection to this air is almost negligible because it's very small because to the air. We know the convection heat transformers is depending on the performance of the working fluid, and the conductivity of the PCM, the liquid PCM, is much higher than that of the air. I think it's about two order higher than that of the air. So the convection of this one is almost negligible. But in the numerical simulation, I think it's also consider the convection of this one, but the amount is very small. So I don't think it will affect the results of the practical application.
Okay, so my second question is because since like this heat exchanger there's many tube PCM other device, since this is very heavy. So my question is compare for the satellites, the other slides like the heat conduction sheets, like the radiator is kind of more the smaller and likely, so this kind of he hits the combustion sheet. So what is this kind of distance advantage, the main advantage? So this is the second question. Thank you.
I'm still not very clear of your question because still have some noise. Do you think about the connecting pipe?
I mean, compare for like the heat radiator, heat conduction sheet, this kind of the tradition of the satellite slides used to remove the heat. So what is your system, this exchange system, the main advantage?
You say that for the practical application, they use the radiator, right? And here I use the natural convection, right?
Yeah.
Is this one? Okay. So because we just want to test the heat performance of this part, and this part, we cannot test it by using just radiation in the ground because we don't have much radiation. The outside environment temperature is very high. in the ground temperature is about 25 degrees Celsius, but in the space it's about -20, I think. So it's much lower than in the environment in the ground. So we cannot use just the radiator by using the radiation heat transfer. So then we think about how to test it and as close to the practical condition as possible. So if we use the forced convection, air forced convection, or use the liquid cooling of this panel, then it will be a very large difference of the radiator. So then finally we choose the natural convection, because the natural convection transfer coefficient is low. It's low, so this will not affect the entire system, even though this one is not the same as this of the actual conditions, but the difference will not very high, because the major heat transfer mechanism will be in this side, but not in this side. So this is the reason why we choose the natural convection. Is this answer your question?
Yeah, thank you very much.
Okay, thank you.
Okay, my last question is that in one slide you said the numerical simulation was done by a student, right? By your student?
Yeah, my student.
What was it? I suppose it was a master degree student.
It's a master degree student, yeah.
Very good, yeah.
Yes, the student is very strong. Yes, I think the student is the graduate from the National Center undergraduate part in our university, and
well, it's to keep him to work to study for PhD degree.
Better than me. I don't know how to use the numerical analysis.
I was saying that you should keep him to work on his PhD degree. Yeah.
No, he's going to go to industry. He will graduate next month, and
I know. Yeah. Right. Okay, good. So I think we will end this session. A very interesting session and very engineering one. Very technical, practical one. And I believe that the Prof. Yang would continue to work on this subject in cooperation with NSPO. And if the audience have any questions or want to ask him, please write to him. And Professor Liang, you have any questions, comments? I cannot hear you. We cannot hear you. Can you open your mic?
No, I just want to say I appreciate this presentation very much, and thank you, Professor Yang, for this wonderful talk. Thank you.
Thank you.
Yeah. So we invite you to visit Central University next time.
Very soon.
Yeah, I'm looking for you.
How your policy changes. And
Right. Yeah, real soon. No, I think we are in deep trouble, but maybe it'll be over very soon. That means. Okay, thank you so much.
Thank you. Bye-bye.
Stephen, yeah, and
bye-bye.
And everybody.
Bye-bye, everyone.
Yeah, bye-bye.
Bye-bye.
Good night. Yeah.